So, oh, sorry.
When you do the plot, use the program, run it, you may see that the case with and without roughness give you similar flow pattern map. Not identical, right? They're just similar. Okay? The chart, whatever chart that we have, like in page 68, that one is for smooth pipe. Okay?
Yes, exactly.
The next chart is also smooth pipe. Every chart, they are all for smooth pipe. Okay? So as an engineer, we have to do calculation. If we cannot do it, we make some assumption. If we can do it, we do it our best. So, okay, simplify method. You make some assumption. You may say that the flow pattern map determined based on the smooth pipe is similar to the case where we determine based on rough pipe. And we keep using the chart. Of course, it's not 100% accurate, it may be 80% accurate. Okay, so keep using the chart. Okay, or
But for formula,
if we do without the chart, you can get HL tutor from the chart, okay, and estimate at each transition based on HL tutor from the chart. And that HL tutor is for the case of assume that everything is smooth pipe, which is not perfect, 80-90% correct, not absolutely correct. Okay, if you want to be very correct as much as we can, another method to do is we start from combined momentum equation, dimensional form. You remember dimensional form, combined momentum equation? Okay, from the, yes?
Sorry, for homework 2, this homework problem 2, you have 2.1, 2.2, and 2.3. What
Okay,
is question 2.1?
2.1,
is flow pattern.
flow pattern.
There's no BSL and there's no BSG.
Oh, you select. I missed several things, not just BSL, VST. I thought I missed just BSL, VST. So you select the point that you like. Okay, BSL, VST, angle, pipe diameter. Whatever you like. Generate the map. When you generate the map, you get your result.
So you expect us to generate just one map, right? Yeah, because
You can generate as many maps as you want.
no,
One map is fine.
in question 2,
So
the
when you
actual
generate
map.
that map, the map tell you, okay, that operating point is this bubble flow. Next, what you will do is check based on your approximation, or you may do the approximation or you may not do the approximation. What is that flow pattern, right? Okay. So when you do the approximation, you may assume, okay, the pipe is rough, but we use X to get H altitude based on the smooth pipe chart. And from that smooth pipe chart, we determine transition A, B, C, D based on the H altitude from smooth pipe chart. Okay. Alternative of this is start from combined momentum equation and use cosec or change the value digit by digit to find H altitude that make combined momentum equation equal to 0, left hand side equal to right hand side. Combined momentum equation that I'm talking about is page 65, equation 3.28. Of course, this is late, right? Put at the back of your name when you sign your sign-up sheet, that you are late, okay? So when we have from combined momentum equation 3.28, so you will notice that that equation has no assumption on the roughness. Okay, it's have tau WL tau WG, tau I, and several other things, right? So tau WL, tau WI, we can calculate based on Colebrook equation. Okay. So when we calculate based on the Colebrook equation, we need Reynolds number. Reynolds number is rho Vd over mu, right? D is a function of H altitude. V is flow rate per area, and area is a function of H altitude. Okay, so Reynolds number is a function of H altitude. So everything in your combined momentum equation is a function of H altitude when we use Colebrook equation. So this means if you want it to be very, very accurate, what we can do is adjust H altitude until left hand side equal to 0. And when you do left hand side, use Colebrook equation. Okay, you don't need to use goal-seek, or you can also use goal-seek. For example, if you don't use goal-seek, you start with 0.1. Okay, and left hand side may be equal to 10,000, right hand side equal to 0. And then you go to 0.2. Left hand side may reduce to 10. And then you start with 0.3. 0.3 may be left hand side equal to minus something, minus 2 or something. So then you know that the answer is between 0.2 and 0.3. So you go back to 0.2 and you change to 0.21. So left hand side may reduce and approach 0, right? If you go beyond 0, you change the digit. So you just manipulate digit by digit, and then you get the result. That is very easy method. Of course, tedious. Yes.
So imagine that you get your HL tilt from the procedure you just explained.
Yes.
Now you want to use that HL tilt to get the flow pattern. Okay.
Okay.
Using the chart, what I understand.
Oh, don't use the chart.
Yes, because if you use
Don't use the chart.
Because if you use the chart, it already assumes that you have smooth pipe, right?
Which chart?
The chart that you get flow pattern from.
Is this the chart that you're talking
Yes,
about?
yes.
That chart, do we assume the smooth pipe?
Yes, sure. Go to
Kind
T
of.
condition.
Yes, don't use the chart.
So if you use the
Because
chart,
the chart may assume
smoothness.
smooth pipe when we calculate X or something. So,
If you go to the T condition,
okay.
T2 condition, okay?
But still works, the chat works.
Yeah, the chart works. Yeah.
This T condition. Okay.
VL greater than something. So all those VL will be Q divided by AL. And AL will be calculated based on H altitude, which is come from solving the combined momentum equation. Okay? And on the right hand side, S, G, all those things will be dependent upon H altitude, which is from solving combined momentum equation. Anders, is this good for you? Make sense?
Yeah, it makes sense.
Not to the extent that you want. Of course, in the exam, you can solve it digit by digit or numerically.
They don't have Excel.
I don't ask you to do that, okay? Your calculator actually can, but okay, I don't ask you to do that, maybe that's too much.
It can, but
It can, yeah.
Doesn't have to.
You can let us bring laptops.
Yes.
No.
We cannot download this from internet or anything.
No.
Dr. Sheng did that, Professor. Please.
Take home exam.
I'm not Dr. Sheng. I don't do that. I don't do the take-home exam. Okay, let me encourage you a little bit. Transition A, B, C, D, Vega already programmed it in the calculator. For example, if Vega get H altitude, Vega can calculate all the transition very quick, right?
I haven't done it with the transition yet, just
Oh, you-
the X, Y, and all of the tutor, like all the.
AL tilde, SI tilde, AG tilde, everything quickly. So this means if we have, but you still have to write the equation in the exam, right? So let's say you read the chart and you want to calculate AL, AG, SL, SG, SI. He can click, or press a button and get everything quickly. Quickly means in a matter of minutes, he finished writing the equation and all those numbers. Done. Okay? Just to encourage you a little bit. He can, so you can too. Right? Who lost the calculator?
Lost?
Do you still have your calculator? On Monday, I find the calculator, the same model that we are using in that room. Okay, in the lecture room.
Oh,
So
let's see.
I think it is one of us. But if you don't have it, go to the office, admin office. Let's talk about homework. Next homework. Okay. Homework 5. And after homework 5, you don't have any homework until the exam. Yes.
It's next.
Yes.
Yeah, so on homework 4, with the last sentence you have the flow pattern is wrong, but the pressure drop calculation is correct.
Yes, what-
The flow pattern is not, okay, the point is not you get the right answer or you get the wrong answer. The point is you realize that what you get from the book is for smooth pipe and it is not the same as the program. That's what I want you to see. Let's say you do the flow pattern, you get program, right? Program tell you is this bubble flow. You do it by hand, it tell you intermittent flow, right?
No.
No, it depends on what value you pick.
Yeah.
It depends on what value you pick.
Yeah.
Yeah.
If you have a low VSL,
So it may tell you the wrong flow pattern.
but
Even if you do that, your answer is still fine with me. I want you to see that it is not the same. And the program is correct, not you correct.
what about
Pressure drop, when you do the pressure drop, you should use your engineering judgment, okay? Do we have a lot of difference between the pipe is smooth and the pipe is rough? If so, we calculate friction factor from Colebrook equation. So when we go back to dimensional form of minus dPdL subscript L, we can start from there, right? And tau, 1/2 F rho V square, that F has come from Colebrook. And for this bubble flow, you may say, okay, no slip condition, lambda, use lambda instead of h. And from lambda, find average h, average mu, average rho, and then calculate average Reynolds number. From average Reynolds number, get friction factor, then get the result. Of course, if you assume that your pipe inclination angle is not horizontal, don't forget the gravitational term. Yes.
So I found that the flow pattern is dispersed bubble flow, and
By program. Flow
by
pattern.
both of them.
Both of them. Okay.
Both of them. I know that it is dispersed bubble flow. So to get the pressure drop per unit length, what do I do? Because we talked about.
Okay. What do I do?
No. The
Just
question,
lambda.
the question here is that we already have talked about this stratified flow, how to calculate the pressure drop.
Mhm.
But for dispersed bubble flow,
Did you talk
I got
about
the
it?
I got the I don't know, a liquid hold of about 90%, 0.9, but when I calculate the no slip velocity is about 0.6. And
Okay.
to
I
me-
have a question for you, Arya. If it is this bubble flow, how do we calculate pressure drop?
we assume that it is due to single phase, then calculated based on the mixture velocity. Mixture.
How good is that assumption?
It's bad.
No, it's good.
No,
It's perfect.
That's what this is.
For this bubble flow, it is perfect.
no slip velocity.
It is
No
perfect.
slip. We have. I calculated no slip liquid holdup about 0.6, but the actual that I calculated was about 0.9.
So you don't like your answer. What did Shoham say?
Sure. What did you say, man?
So for this bubble flow, okay, the fact is there is no slip between liquid and gas phase. Because of the turbulent flow, liquid break gas bubble into very fine bubble, and there is no slip between liquid and gas phase. So no slip liquid hold up is the actual liquid hold up.
But
Okay.
based on this equation, the governing equation, I
Straight.
calculate the
Yeah, but again,
I calculate the velocity of gas about 72 meters per second, but for my liquid it was 10. So obviously there is slip.
72.
Yeah, I had everything very
72 meter per, okay. First of all, in order for us to assume that the flow is incompressible, we have to go slower than speed of sound. A lot slower than speed of sound. 72 is kind of high, okay? Please check your calculation. I have 2 students, including the one that come late, tell me Reno number equal to 18. Sometimes that happens, okay?
The case, what I'm saying is that so it's 72 is hot, but when the velocity of my gas is a lot higher than the velocity of my liquid, based on the liquid holdup I calculated.
Liquid hold up.
If I
Is that
want-
from lambda?
No. The
Ah.
one from the governing equation.
Governing
Because
equation
it's
is for
actually
stratified flow.
What typically?
Question 2, I asked you to do stratified flow case. Calculate pressure drop per unit length. Then assume that it is stratified flow and then calculate pressure drop per unit length again. For that, you will realize what happened if we get the wrong flow pattern, but do the right pressure drop calculation. What is the difference in the answer?
Oh, so you're saying that even it is dispersed bubble flow, when we have to calculate, to
Even
know
if-
the flow pattern, we should calculate the HL tilt. Okay?
Yes,
But
but we
we
don't
can't
use
use it
that. For pressure drop calculation,
We use
to,
no slip.
let's say we have this bubble flow. We do the flow pattern check, transition check, right? We do the transition check. And at the end, we say, okay, it is this bubble flow. What do we do next?
Forget about the HL.
Next step, yes, you come there and you keep talking. Please, come see me after class, okay? So when we have this bubble flow, we check the transition, we check this bubble flow. So next step is, we forget about HL that we get from the stratified equilibrium model and use lambda to calculate average density, average viscosity, and then calculate it as a pseudo single phase. And it is going to be correct. Yes.
Why can't we use the HL wave concept?
Because it's wrong.
It's wrong.
HL though, that we,
No, not to
capital H,
capital H.
that we get from the chart, Title Doppler model. Title Doppler,
Basically, we're doing exactly what you've done, we're writing HL theorem, right?
use the chart in page 68, yes.
We just use it, that's just.
Or use the combined momentum equation and
Right.
get solve numerically and get H value.
So.
And we check, eventually we check and found that it's just this bubble flow.
Yes.
I said forget about H that we get.
I agree,
After that-
Agreed.
Why is
What I'm
that?
asking is, that's not the problem.
Okay.
What I'm asking is the dispersed, if it was actually, if we calculate using the dispersed
Mhm.
method, why would you neglect the HL, the actual hold-up that you've gotten and use?
Okay.
Because the
The
assumption.
question is, when it is this bubble flow, why do I neglect the hold up that I get and use no slip hold up instead?
Yes, that's what the question is, because
Okay.
that gives you,
Yune, do you have answer? Come on.
Because they assume the single phase flow is the
I-
same.
that's-
Vega, do you have answer for me? So if I put it in the exam and ask you that, okay, I use Title Doppler model, I get H altitude, I get capital H, I found that it is this bubble flow. Why do I disregard all those H altitude that I get and calculate, use a no slip hold up? You don't have answer?
Not any good answer. So.
You're wishing.
I don't know either.
Sweater.
Because that one is for two.
Okay, let me ask you this. Combined momentum equation. We have tau I, right? Do we have tau I in this bubble flow?
No.
Oh, okay. So we have SG. Do we have SG in this bubble flow? No, we don't. So what Tatadala did is assume that it is stratified flow first and check if it is stratified flow or not. If not, use a pressure drop calculation approach that is valid for each particular case.
Yeah, I agree. No doubt in that.
We have to neglect HL
HL
or hold up that we get from combined momentum equation because that is for the case where we assume that it is stratified flow. So if we assume that it is stratified flow, we get a certain hold up. But if we assume that it is this bubble flow, we have another hold up, right?
Yes.
And if it is this bubble flow, we use this bubble flow calculation method.
I have one question.
Yes.
So after we get the flow, when we calculate the flow pattern step by step A, B, C, D, right? After D, it says either it's intermittent or
This bubble flow.
dispersed. So how do we know that it's exactly dispersed bubble flow after D? Because it's either one, right?
T will be greater than the.
T greater than 8 inches to
Above D.
We use equation 3.62. The transition to this bubble flow will occur if Ft greater than Fb or Vl greater than this whole thing.
But what
3.62.
But what if you're doing a calculation in dimension form?
Dimension form, yeah. Vl greater than 4ag g cosine theta over SIFL. Page 73. 73. And near the bottom. That is to check transition D. Transition D is
Yes, I think this one, but isn't it this one for transition?
transition D will tell us exactly whether it's this bubble flow or intermittent flow. Okay. Oh, let's talk about homework. What? 5? Which available already, but you don't have to worry about it yet. It's just due next week. Okay. And the next Wednesday, I have to read. And next Wednesday we don't have homework 6, but you have time to prepare for exam. It's open book. You can bring your cheat sheet or something.
What is the exam?
Huh?
What is the exam?
As promised in the syllabus, which is Monday,
I thought it was
after
the 17th.
next.
Yeah,
Yeah, it's 17. Yeah,
Okay.
17. 17 is
Yeah, Monday.
Monday after next Monday. 17. That's 17. What do we cover? We will cover everything until 10. Monday 10. That's for 17 exam.
So we are slugging the exam.
I don't know, I haven't made it yet. We will see how far we go. Okay, take a look at homework 5. This whole thing will not appear in the exam because it's too long and it cannot be done. Just use that calculator actually can do, but it takes too long time. What I asked you to do for homework 5, question 1 is to get the expression of C versus Renault number SL. We did this in class. I did that in class. Okay. I want you to do it. I want you to show me the derivation, which you can copy from the slide, of course, and show me your plot. The plot between small c and Renault number of liquid slug. Okay, RELS. Okay. For turbulent flow case, you still remember, right? In addition to that, I want you to plot the velocity profile for the case of you assume this bubble flow inside the slug body, right? So plot the velocity profile inside the slug body. It is the same as single phase. And the formula is given. CV plus. So it is just a formula, don't worry about it too much. But you have to come up with your own assumption, like what is your pipe diameter, what is your average liquid flow rate, what is your fluid property. You have to come up with all that in order to plot the velocity profile. Unless you plot the velocity profile in the dimensionless form. If you plot the velocity profile in the dimensionless form, you may have to come up with some velocity or something. Okay, average velocity. So plot the velocity profile. Use that formula. It is the same as single phase flow. Okay, and question 1 we do together in class already, so there's no excuse that you cannot do. Okay, you don't even have to do any integration. Because I integrate it for you already, I get a final form. But you will show. If you just copy it from the lecture, of course you cannot do anything because you don't understand it. Okay, so you may actually have to go through it. Question 2, it is easier, but we have never done it. It is laminar flow. We assume that inside is kind of fully dispersed, but laminar flow for the case of flow in the liquid slug. And you will want to calculate what is the shedding fraction. You remember shedding fraction? X equal to integrate everything minus the part that advanced with the flow. You will do that for me. Velocity profile, it is also given. Okay. We have two forms, delta P minus delta P r squared over 4 mu, and it's a parabolic shape, right? So you will do the same thing that we did in class, except this time it's easier. Easier doesn't mean it's easier because this is unseen, okay? Any doubt? Siri, you good?
I'm good.
Okay, easy enough, right?
How many hours would it require?
Oh, how many hours does it take? Let's go. I don't expect it to be longer than 6 hours.
How many hours did you think we spent for last homework?
Yes, Professor, what was that?
Jesheng, how long does it take for you to do it? For last homework?
She said
very smart.
6 hours.
6 hours. Yeah, perfect. Perfect. Yeah, 6 hours.
It was,
Like average.
it was way more than 6 hours.
Average. Yeah, I think she is kind of.
No.
So keep in mind that everything that we do here, we want to get pressure drop, just that, and some characteristic inside the slug flow. It is important to get the characteristic of slug flow, like film shape, liquid height, film length, all that, because it is related to heat transfer. Okay, and heat transfer is related to hydrodynamic, of course, because your viscosity is a strong function with temperature, right? So you need to know temperature. Let's check the process that we talked last time again. So I give you V plus. Notice that I select just in the middle. In the middle, velocity profile look like this. A, which is 5.57 plus 1 over kappa, natural log of Y plus. Y plus is defined from frictional velocity. Frictional velocity is square root Washer stress over rho. Okay, that's frictional velocity, and Y plus is Y V star rho mu. So this means when you do homework, you have to come up with your own rho, come up with your own mu and velocity, and you have to make sure that your Reynolds number is more than 4,000. Okay, if your Reynolds number is less than 4,000, it's not turbulent flow. Then it is wrong. Okay. So what we have done is do that integration. This is governing equation for x, and we have c equal to x over some parameter, right? So we do the integration. We have c equal to 1 minus all this, which is x over those parameter. substitute, you have C over here, right? Substitute HLLS, AP, rho L in it. We do the integration, then we get expression for C. Keep on doing it. There has to be some change of the variable or something, calculus 1, okay?
So, quick question.
Yes.
The assumption is the slot body would always be turbulent flow, then the tail threading it would that be also be turbulent or be laminar?
No, we will, depending on viscosity, this is very simplified model, so it assumes everywhere is turbulent. Everywhere is turbulent, and this is kind of true for air-water flow when translational velocity is very fast. You cannot even see it, that's very fast. But if you have viscosity on, yes, at the back, even at the front, it may not be fully turbulent flow. It may be laminar flow, like transition to turbulent, not fully turbulent, and at the back, maybe laminar flow. Okay. So this, you see the trick here. The trick that we have is, okay, let's support that. The trick that we have is, I change the limit of integration from RP to RP plus. And instead of Vs, I use V plus. Instead of R, I use R plus. Change the variable, then the integration can be done somewhat easier. If you cannot do the analytical solution, use numerical solution, okay? Numerical solution is like you draw trapezoidal shape under the curve, add them together. Okay, but try to do analytical solution. If you don't know integration formula, open Wikipedia. Okay, open Wikipedia. So we do this integration. You see this V? V is, I plug that in. You see this V plus, I put that V plus in here. Okay, I put that V plus in here. And Y plus, I put the expression for Y plus here too. Okay, this is the relationship between Y plus and V plus. So V plus is a function of Y plus, right? So we have to express V plus in terms of Y plus, which is V plus equal to this, or Y plus equal to something like this. Put it back, do some trick. Of course, you will review more when you do the homework. So I put it back, and I just put V over here. That is V, right? That is V. Multiply them together, get this form. Get this form to do integration, and then integrate it. Integrate a natural log or something, and then get the result. After getting the result, plot it. Just that. You will do it, okay? It is not just copy from the slide, because you need to understand which term is which term, okay? In order to plot. Otherwise, I don't think you can plot. So question 1 is the same. RE, Reynolds-North liquid slug is rho L VMD over mu. Okay. You will plot and you will show me that whether you get this or you get the curve like what is in the book. Okay. Do you actually get that S shape or you just get a straight line? Note that this is in semi-log, right? This is log scale, that is linear. Okay. So you will do the same thing for laminar flow. I asked you to do laminar flow case because sometimes you can have slug flow, but it's not quite turbulent flow. So your result will be within the limit between laminar and turbulent, right? So one extreme is it is turbulent flow inside the liquid slug. Another extreme is it is laminar flow inside liquid slug. So your C value should be between that two extremes. However, you will notice when you derive it, you assume that it is fully mixed between gas and liquid phase. If you have horizontal flow, gas bubble can stay a little bit on top, and we have more liquid at the bottom, right? So it also depends on how it distributes. This way of calculation is a rough estimation. Okay, we already, so this one becomes the homework, right? This is the homework. Okay. Hydrodynamic of liquid film. Last time who cannot do the quiz? Yesterday quiz? You want to do it again?
Yes.
Okay.
We give it 20 minutes.
But you have to give more time. I know you should not be counting down.
You
by
don't want to do it
5,
again?
4, 3, 2, 1.
Just disregard that quiz.
Oh, I will drop 2 quiz, right?
Yeah, that's fine then.
I will drop 2 quiz. So, who finished it last time?
8 people did, so.
Yeah, Anders finished it
What
last
did
time,
you
right? So, can you finish it again this time if we have it? Yeah, if you do it again. You don't know for sure?
Yeah, I think so.
Okay, alright. So,
No.
Jeshen, did you finish it?
No.
Who else finished it? Come on.
So 8
That-
people finished.
But professor, in given time, in order to finish, you have to skip some parts of derivation.
Yes?
Well, the objective of that quiz, is it to finish it in the fastest time or to understand the equation and you can do it?
The objective of that quiz is to train you to be able to do it within the time that you should do it.
Oh, that's the reason then. Yeah, that makes sense.
The reason is to train you to get to the speed of every other people when they do it.
Speed of Ocean.
Speed of every other people that they do it. Of course, you have to practice, right? And if you know beforehand, you should be able to do it within that time. If you practice enough. It should be embedded in your brain. It should stay in your brain and you do it very quick.
No sleep, right?
Yeah, this is going to be-
How can I apply the possibility like option to have more time?
So, Anders, if we do it next Monday, you ready?
Next Monday?
Yeah.
If you say this quiz, then I will.
Or if we do it 11 a.m. today, you ready?
Oh,
Not today.
Or next Wednesday, you ready?
next Wednesday, yes.
I haven't printed it out. I can print it very quick. Got it today?
No, let's do it.
Let's do it on next Wednesday, please. Or next Monday.
Next Monday.
Next Monday.
Okay, let's do next time sometime. I mean next week. Alright, we finished the shading process. Okay? And we will talk on hydrodynamic of film. We have about 6 minutes and we will continue at 11 o'clock. Okay? So for hydrodynamics of the film, the trick here is we use moving observer frame of reference. Okay, so when we use moving observer, we said it is a translational velocity coordinate system. Translational velocity of coordinate system. So we move with the Taylor bubble. So when we move with the Taylor bubble, the problem becomes steady state. Okay, steady state. When we have steady state problem, we define VF. VF is kind of velocity of the film for the moving observer. Okay, velocity of the film for the moving observer, which is VTB minus VLTB. And from previous equation, we know that it is x divided by rho A h, right? That is from mass balance. You recall this one? We just did VTB minus V something multiplied by H something equal to VTB minus V something. So the mass balance at the slug front or slug tail. So we have VF. Okay. Akin VF, is that the same everywhere in the film? Yes or no? Based on that equation.
I think yes.
Okay, what about VLTB? What is VLTB?
That's the Taylor bubble
Velocity of liquid phase inside the film,
Taylor
right?
bubble, yeah.
Is that the same everywhere? Yes or no?
No.
Maybe no.
Maybe no. So at the back of the slug or at the slug tail, VLTB is fastest, right? Away from the slug tail, it approaches zero. Of course, if you have incline, it can move backward. It can be negative, right? So VLTB is not constant. What about VTB? VTB, is that the same everywhere in the film?
No.
What is VTB, Akin?
That's the table bubble velocity.
Yeah, velocity of the interface, right?
Yeah.
So if the interface at the front moves faster than the interface at the back, Taylor bubble length will be expand. Will expand, right? So if it is fully developed or in the lab, you don't quite see Taylor bubble expand. Taylor bubble shape stay the same. So the velocity of the interface is the same everywhere.
When you say velocity of the interface, is it not just this edge?
That interface.
Okay. But there's also the velocity of gas inside the interface.
Oh, I'm not talking about the velocity of gas. I'm talking about velocity of the interface. Velocity of the gas inside. Gas moves slower than the interface. Okay, and okay, we have some kind of mass balance. Okay, and that make you see that liquid velocity inside the film is not the same everywhere. So do the gas phase. Gas phase should not be the same everywhere either.
But the
Velocity of gas inside the Taylor bubble should not be the same everywhere. And we should have, you will see in a minute why it should not. Okay, but let's do the liquid part first.
So
For the
VTB is not the same.
VTP is the same everywhere. So you see that X, right? This means X is not this. You see X over HLTB. HLTB is not the same everywhere, right? Hold up, change with distance, right? You can do the same thing for the gas phase. You remember, for gas phase, you would use VTB minus VGTB multiplied by alpha TB equal to VTB minus VGTB multiplied by alpha LS. And you can get X and it will be divided by alpha something. And that alpha change with distance. Alpha is a void fraction, 1 minus h.
with rho g change with distance as well.
What?
With rho g change with.
X?
If you say for the liquid it's constant, but the rho g would also change, right?
Rho for gas?
Based on the fact that you have the shape and various varying velocity.
You may assume that the change in density is negligible, which is the assumption that Taitobani and double Hubbard use. No compression or no, it's not expand or shrink. So X, how about X? Akin, okay. X change with, okay, let's change. Nyamli, X change with distance or X stay the same?
X will change.
Okay, let's go back to the definition of X. So X pick up rate, okay, shedding rate. So Vs is the same, right? Everywhere inside the liquid slug. What about HLLS? Do we assume that it is the same everywhere inside the slug? Okay, AP the same everywhere, L the same everywhere, VTB is the same everywhere. X equal to, look at the term on the right. VTB minus VS multiplied by something. All those are constant. What do you think? Is it make sense to you to say X is constant? Based on that expression. The one, this part on the right hand side.
Yeah.
Okay. So X is constant. You don't like it? Akin, okay, what did you say?
The HLLS, that's the
Change? Or HLLS?
yeah, from the shape of the
HLLS is liquid hold up of liquid slug.
Slow.
Is that not changing? Look at the
In
shape.
the slug body.
Yeah.
So in the slug body, that is slug body.
Okay.
See that slug body? The assume is fully mixed. Of course, if you are at the boundary and close to elongated bubble flow, it's not going to be that fully mixed, right? But in this case, they assume that fully mixed. So HLLS is constant. Okay? So this means X is also constant. Pickup rate is constant. It's the same as shedding rate. It's 9:50. I'll turn off the camera and see you at 11.